Okay, so why don't you find that set 4 from the summer packet? Yeah, and if anyone has, it's my next thing I was going to say, if you have the parent signature sheets, if you want to throw those in the green bin, remember, they're due tomorrow. Most of you have already turned them in. What else did I want to tell you guys about? The summer packet test will be next week. I'm not sure exactly what day it will be, and it will just be on the concepts that are in that packet. So if you're struggling with something, find me so I can help you, or find a buddy that can help you. Use the solutions online. So I'm going to show you a couple things just to make sure. I know I've showed you already, but once you get into course sites, the answers to the summer packet are here, worked out, not just the final answers. If you didn't get a 5 on that intro to course sites quiz, that short little 5 question, and you want to do it again, that's fine. I opened it up, so just let me know so that I can change your score and add another point. It was a 10-point assignment, so if you want all 10 points, just tell me that you did it again. If you look in the assignment sheet section, I will have posted probably later today, if not early tomorrow, week 2, and that's where you'll get the assignment sheet for next week. Under taped lessons, each day I put a little blurb. So yesterday, I did 2 videos. I split it so that someone wasn't watching it through the warm-up, that little quiz that I gave you. So sometimes I'll do that. And then if you need to make something up, I'll say, we took this warm-up quiz, come in and take it. But the assignment will still be on your assignment sheet. But that's a little blurb. If you go into the YouTube channel, because this was not working, so I stayed yesterday and kind of made sure everything was working. These are where all the lessons will be. I was saving them, and they weren't going in here because I have different Google accounts for different things. So I think I got it squared away. All right, so that's where those taped lessons are. Any questions on Blackboard, the videos? No? Okay. All right, pick a good number from set 4. What number do you like? Do you like, I think they picked 7, I don't know. 2 and 4 are in the video. So let's do one that's not, okay?
Could we do 6, 4, 7?
Yeah, 6 or 7, yeah, that works out. And what I'll do is I'll go through, and I tried to do this in the video as well, and really go through and explain why you do certain things that you do. And it doesn't really matter. 6 and 7 are both good. 6 is actually a little harder because there's an extra fraction. Okay, so want to tackle that one? All right. So you might look at this and go, what? What is this? Well, these are going to be how our answers look like when we take the derivative of something. So we might go through and take the derivative of a function, and we may end up getting something that looks like that. And what we have to do is simplify it. And what is considered simplified are questions that have no complex fractions, meaning no fraction and a fraction, and no negative exponents. Okay, so that's the goal, is to get it simplified. So the first thing I'm going to do is look through it, and I want you to realize that this right here is one entire term, plus this is another entire term. So it's like x squared plus x, except for it looks a whole lot messier. Okay? It's one term plus another term. So what we have to do is factor. So in this case, I factor out an x. You want to tell me what is in common in both of those terms that we can take out? Good, a negative 2x. Now, someone may not have taken the negative 2x out, and they may have distributed, and then you would have had to do more work because you would have simplified and then had to take it out anyways. So I'll just take it out now. And then do you notice that there's a 16 minus x squared quantity? One is raised to the negative a half, one is raised to the half. Now I'm going to tell you to take out the one that's raised to the negative exponent, and I'll tell you why in a couple minutes, okay? So I'm going to take out the one that's to the negative a half. And then remember, when you are factoring, essentially you're dividing it out. So I am actually dividing this first term by negative 2x times 16 minus x squared to the negative a half. And I'm dividing the second term by that same thing. Now, you don't have to write that step, but in trying to explain it, I want to tell you that that's what you're doing. Okay? So far, so good? All right, so if we divide this first term, tell me something that's going to go away. The negative 2x's, right? What else? 16 minus x squared and negative 1/2, gone. What else is left? 1/4 x squared. That's it. Now, if I would redistribute, just to check myself, I'd see that I have a negative 2x, a 16 minus x squared to the negative 1/2, and a 1/4 x squared. Now I'm going to do the second term, okay? So when I divide the second term, you'll see the negative 2x cancels out. You have the 16 minus x squared to the 1/2 on the top over 16 minus x squared to the negative 1/2 on the bottom. So let me remind you with properties of exponents. If you had something to the 1/2 over something to the negative 1/2, like let's just say it's an x, you'd be able to do that with no problem, wouldn't you? What would you get? What's x to the 1/2 divided by x to the negative 1/2? What do you do to the exponents? Subtract, so 1/2 minus a negative 1/2 is 1. So you would end up with x to the first. See that? Okay, so when we do the same thing here and we divide 16 minus x squared to the 1/2 divided by 16 minus x squared to the negative 1/2, we're going to get 16 minus x squared to the first. So, let me write it on here. So plus 16 minus x squared to the first. Do I really need to write that in parentheses or with an exponent or anything? No. Okay, so far? All right. Now, if I redistribute, I could check my work to make sure that's what I would get. Okay, now I'm going to clean things up a little bit. I have negative 2x. This thing can actually go to the denominator because this is one whole thing being multiplied. Then we have this and this. This negative exponent can go to the bottom. We could keep it the 1/2 power. You can make it the square root. It doesn't matter. This next part is still on the top, isn't it? Still in the numerator. I'm going to subtract and make it negative 3/4 x squared plus 16. Big fraction bar, because this is being multiplied, so this is one big fraction and this is that denominator. Now the reason I took out the negative exponent quantity was because then I could put it in the bottom and get rid of the negative exponent. Now I have to clean this up because this is considered not simplified because there's a fraction in a fraction. Okay? So in negative 3/4 x squared plus 16, I'm going to make 16 be 64 over 4. This is why this problem is harder than number 6, because you didn't have to end up doing this. 64 over 4, what can I factor out of 3/4 and 64/4? A fourth, right? 3 doesn't go into 64, so I can't do that. Can I also factor out a negative? So I have negative, and then I have 1/4 3x squared minus 64. Now, if you get stuck with that step, what you can do is go to the side. You're taking negative 3/4 and you're dividing by a fourth. So if you have to go to the side to think that means negative 3/4 times 4 over 1, certainly do that. I always like to check when I do these just mentally to make sure, do I really get negative 3/4 x squared plus 64 over 4? I do. Now the negative times the negative will cancel out. And it's still a complex fraction. I have 1/2 x. But isn't 1/2 x the same thing as 1x over 2? Isn't 1/2 x the same thing? Okay, so that 1/2, when I put it on the top, I'm going to do 1/2 x. It's still a complex fraction. So this 1/2, I'll just make it 1 and I'll drop the 2 to the bottom. So x times the quantity 3x squared minus 64 over 2 square roots of 16 minus x squared. Okay. And that would be it simplified. There aren't any complex fractions anymore. There aren't any negative exponents. So that's like one of the hardest ones. I also in the videos do question 2 and question 4. So if you need a couple of those, because once you get it, there's like a point where it clicks and you're like, oh, that's what I'm doing. But it does take practice, so you have to practice a couple of them.
Does that have to be rationalized?
No. Yeah, good question. Nope. We don't care. There's a radical on the bottom. We don't have to rationalize this year, especially if they're variables. Okay, if they're variable, then we didn't do that before, so we won't do that. All right, any other questions on that problem? Okay, so I encourage you, if you need some more help with it, to do examples 2 and 4 of the video, just to kind of walk you through again how to do a problem of that type. And we will see them. Because we can have negative exponents or complex fractions, we always have to simplify our answers when we take derivatives. And when we do multiple choice, they do that as well. So we want to be able to do it. Okay, what we're going to do next, I told you the summer packet test will be next week. And again, it won't have anything on the test that's not in that packet. We're going to go over the homework from Trig. Okay, what we'll be doing is we'll be having a homework quiz on it next week, or maybe Friday. No, Monday, I guess. I don't have tomorrow on there, so I'm not sure when it is, but we'll do it after we go over it and we have time. And what it basically is I'll just say from your Trig homework from pages, whatever the pages they were, write down all you have for these numbers. So if you have any on your list that you didn't get right, you want to correct, so that when I ask you that, I'm not asking you just to have your homework done, now I'm asking you to have it correct. So let's go over any questions that you had from the homework that was due yesterday. So the homework that was due yesterday was a trig assignment. And it started with 1 to 7 odd. What numbers are on your list? Which ones can we clear up? And I would encourage you to grab a pen. If you don't have one, you're welcome to grab one. And anything that you missed, you want to do in ink. Okay, so that you know right away. Check it out and see if there's any questions that you had. Number 5B. 5B, was this one that asked change it to radians? I think change from degree to radians. Okay. I believe, and it's good that you asked this one, I don't know if they put both answers, but you really wouldn't need the decimal approximation one. 150 degrees, I know, is 5 30s or 5 pi over 6. But you wouldn't need the decimal for it because it's one on our unit circle. Okay. What other numbers? Anyone need 7D? That's the one that I thought was probably one of the ones you might need. 7D gave us an angle in radians. How do you convert it to degrees? Multiply by, yeah, good, 180 over pi. So you get rid of the radians. And how many decimal places do we always round to unless told otherwise? 3, okay? So I don't know if this packet adhered to the 3 decimal rule. So if it didn't, we want this number, okay? What else? 11B. Okay, so 11B tells you there's this angle. So there's a point on that's given, -12, -5. That's not on the unit circle, is it? How do you know that?
It gives you the x and the y coordinates, and the x is the side.
The sides, and they're not ones you recognize, right? For the sides of the triangle. Why else? So they're not root 2 over 2 or root 3 over 2 or a half. Why else? How else could you recognize it?
The radius of the unit circle is 1.
Good. The radius of the unit circle is 1, and this radius is 13. Okay, so you want to build a right triangle. Theta is that big angle in quadrant 3, but we're going to steal the information on theta prime, the reference angle. So So we're just going to build a right triangle. They give us the lengths of the sides. We can figure out the hypotenuse, Pythagorean theorem, or that's a special Pythagorean triple if you know it. And then you're just going to use sine, cosine, tangent, SOHCAHTOA, and then the reciprocals. Does that make sense on that one? We okay? Anything else? Okay, then last night, so this is basically what you should have done in your notebook. You should have examples 1, 2, and 3. Doesn't really matter where, if you did them at the end or the beginning, it doesn't matter. And then those problems, 1 to 7 odd, blah, blah, blah. And then last night, you have examples 4, 5, 6, and 7, right? And we're going to talk about some of those after we do a few notes, and we're talking about solving trig equations, because then we can go back to those examples in case there were places that you kind of didn't know what they did. Now, when you do those examples, you can muddle through and write down what they have. But what you want to do if you don't understand it is mark exactly, this step, where are they getting it? And then that way, you know, when we go over it, we'll know exactly where your question was. Does that make sense? Okay. All right, so we're going to do that, and then we will look at those examples. And I want to point out one thing I threw in your packet. When I find goodies, I just throw them at you. So if you look at 26 and 27, I found an algebra resource. And since we're doing prerequisite information, taking all that stuff that's in your brain from Algebra 1, Geometry, Algebra 2, and Honors Trade Pre-Calc, I found a nice page that has all these Algebra 2 things on it. So I'm going to go through it because I'm going to tell you what things you don't need for this course. It doesn't mean you won't need them for Calculus Part 2, but just for our course. So this is in the packet on 26. Good, 26. So exponents, good. Complex numbers, no, we don't do them. So if you want to put like a little X through that box, we don't deal with complex numbers this year. Logarithms, yes, and it's probably one of the weakest spots that we have, one of those weakest concepts that we come in with. So logarithms and properties of logs, very important. Factoring, yes. Exponential functions, yes, they're the inverses of logarithmic functions. Quadratic equation and completing the square. So it gives you a nice little resource because we're going to be throwing problems where we have to solve it and we have to do those, and they expect us to remember how to do it, so this is on here. Variations, different types of variation, direct, inverse, varies jointly. We'll see those words. Absolute value and inequalities, those are all good things. Then on page 27, they give you a little review on radicals and simplifying and different types of functions. Those are all good. Working with rational functions and rational inequalities, that's all good. We won't do sequences or binomial theorem. That is BC. There is a chapter specifically about sequences and series. We'll use equations of circles and complex fractions. And then on page 28, this just kind of was a nice review of all the types of functions that you've learned throughout the years. And they're all good. The only ones you don't really have to have memorized anymore are your ellipses and your hyperbolas. Now they may give us some equations that are ellipses and hyperbolas, but you can still get it without knowing it was an ellipse. We'll kind of talk about, hey, if you remember that's an ellipse, and so yes, of course it has vertical tangents and horizontal tangents. So we'll talk about things like that, but you don't have to have those memorized. Okay? Any questions? So just a little algebra resource for you. Okay, so let's take a look at some notes. And what I would like you to do on page 22 is to try the first two examples. So do the first one, and then the second one I want you to look at and go, it's kind of similar. So it matches that. Okay, so what do you think? That first one, what family on your unit circle has a cosine of a half? Which one is it?
Pi over 3.
Pi over 3 family. So sometimes if I'm asked a bunch of trig stuff, I'll just put down some of my memorized stuff from the first quadrant. And I remember this one's my pi over 6, this is my pi over 4. The cosine is the x coordinate. It's not, like those don't work, so I know it's the pi over 3. So family's pi over 3, where is the cosine negative? Which quadrants? Yeah, and 2 and 3. Good. Now, if you want to, you could do a road map like pi over 3. I know this is 3 pi over 3. Sometimes that just helps people go, oh, it's got to be 2 and 4. Okay, so I'm going to write down the wrong answers. You tell me why these are wrong. Missing some stuff.
Beneath the plus 2 pi n.
Yeah, I am missing an infinite number of answers. So I'm infinitely wrong. Okay. So if they had said, what are the solutions in 0 to 2 pi? I got it. Those are it. They're specific solutions. Does that make sense? But general solutions will capture all of those coterminal angles that end back at 2 pi over 3 and 4 pi over 3. So we're going to do theta equals 2 pi over 3 plus 2 pi. You can use an n or a k. Those represent integers. Integers are positive and negative, so it'll take into account if you subtract or you add. And then 4 pi over 3 plus 2 pi n. Any questions on that one? Okay, so what's different on the second one?
Not just the sine of theta, or the cosine of theta.
Yeah, it's not just the cosine of theta. But if I have done all that work, can I use some of that work to answer this next one? Right? Wouldn't I have to go through the same thing? Unless some of you are thinking maybe I could use an identity. Anyone thinking that? Okay. And would there be an identity that might work for us here?
Use the double angle.
We could use a double angle one. You could change cosine of 2 theta to, you know what it is?
2 cosine squared of theta minus 1.
Good, 2 cosine squared theta minus 1. You could also change it to, there's a one that will put it in terms of the sine squared, and one that'll put it in terms of both cosine squared and sine squared, and I'll show you where those are today. So we could do that, and then get positive and negative square root and get answers, okay? So that's another way, and we're gonna do one that uses an identity, so we'll hang on, and I'm gonna do this one this way, but that is definitely another way. It's very cool, because there's sometimes lots of ways that you can do a problem and get the same answer. If I've done all this work and thought about this, and I already know that 2 pi over 3 and 4 pi over 3 are my specific solutions, all I'm gonna do, after I still have to think through all this, but instead of theta equals, we can write 2 theta equals 2 pi over 3 plus 2 pi n. And that what would you have to go through and do to solve for theta? Divide by 2, yep, and if you're dealing with fractions, instead of dividing by 2, you could also think of it as multiplying through by 1/2. So there's one set of solutions, pi over 3 plus pi n. You're gonna have more solutions on this one than we would on the first one. Now, how I would get specific solutions after I do this other one, I'll tell you in a second. So let me do the other one. 2 theta is 4 pi over 3 plus 2 pi n, just so I don't forget this guy. Those are general solutions, and we answered the question because they didn't ask us for specific solutions. But now if they say, hey, give me the specific solutions from 0 to 2 pi, you start by letting n be 0, pi over 3, 2 pi over 3. Then you let n be 1, and you figure out your solutions. When you let n be 2, we don't want to. Why not? If I let n be 2, I've gone past 2 pi, haven't I? Okay, so I wouldn't, if they said from 0 to 2 pi, I wouldn't need those. Any questions on that one? Okay, remember those? So if it's a multiple angle, a lot of people kind of get very nervous if there's a multiple angle there. But what you can do is just solve it as though it's a single angle. Then when you write your general solution, if it's 3 theta, you'd put 3 theta equals. Okay? So what about the next one?
You were using double angle here.
And what is that one? What sine of 2 theta equal to?
2 sine theta times cosine theta.
Good. That is your first identity that is super important. I don't know why they love that identity. We're going to see it when we do derivatives, when we do integrals, when we solve equations. It's just their favorite one. It's the one I see the most. Okay? Now what? We're going to be really careful that we're using good algebra. So before you answer the question, think about what would you do if you had something like that? What would you do?
Would you divide out the cosine?
If we divide out, can we do that here? Can we divide out an x when we're solving an equation?
Right.
Why not though? Because we're going to do a problem where you can divide and one where you can't divide, and I want you to know the difference. Why couldn't I just say, let's get rid of those cosines?
You would be missing.
I would be missing solutions. You got it. Exactly. Okay? So we have to get this equal to the most beautiful number. It's the only beautiful number that there is. It's 0. Okay? Why it is the perfect number is when we go to solve this, okay, we're going to get 2 factors. Because what can we factor out? A cosine. So if I factor out a cosine, I now have cosine of theta times some other number, 2 sine of theta minus 1. If I know 2 numbers, and you don't, but I tell you their product, so I'm thinking of 2 numbers, their product is 0. Do you know one of my numbers? 100% sure? Okay. Now I'm thinking of 2 numbers, their product is 1. What are my numbers? Negative 5 over pi and negative pi over 5? Is that what you were thinking? How many ways can you get 1 by multiplying numbers? Infinite. How many ways can you multiply 2 numbers to get any number other than 0? Infinite. So 0 is the only number you can ever use to solve ever, ever, ever. It's called zero product property. That's the only thing you can do. So we have to get it equal to 0. We're going to solve this guy and solve this one. Now when we talk about showing work, like there wasn't anything I could skip yet. Okay? There aren't any steps I can skip. This I can skip. They know we're smart and we can maybe do sine of theta as a half. Some of us like to show those steps, which is absolutely fine. It doesn't matter. But now we need to think of our unit circle. Where's the cosine 0? Where are the x's 0? At where?
Pi over 2 and 3 pi over 2.
Yeah, pi over 2 and 3 pi over 2. Let's write these in general. How could I write them together as 1? Pi over 2 plus pi n. Yes, because they're 180 degrees apart. Now, could you write it? People will ask, well, what if I forgot that and I did pi over 2 plus 2 pi k, or 2 pi n, and 3 pi over 2 plus 2 pi, or plus 2 pi k, or 2 pi n? That's fine. It's redundant because you're going to get, but it's okay. It's not wrong. Sine of theta is a half. What's our family? Pi over 6, right? Pi over 6 family. What quadrants are signs positive? 1 and 2. So we'll get pi over 6 and what's the other one? 5 pi over 6. And if I wanted them in general, I can't write those together, can I? Okay. So why couldn't I start that by dividing by cosine on both sides? I would lose solutions because I'm totally eliminating it. Okay? Now look at the next one because I'm going to tell you can do something that I just told you couldn't do. But I want to know the difference. What do you think?
Is that because you're not completely dividing out the things with some of the way?
Exactly. You got it. Good, 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 good. So if I divide this by what? What do we want to divide this one by? Both sides by, it really wouldn't matter. We like tangent better than cotangent. We're going to have to do tangent anyways eventually since it's the reciprocal. But I can divide these by cosine because I'm not dividing it to get rid of it. I'm dividing it to turn it into something that it's equal to. Does that make sense? So you can't divide both sides by an equation to get rid of something, but you can certainly divide it to change it to an identity. Okay. So where is the tangent 1? What family?
Square root of 2 to the square root of 2, but they both have to be the same side, so it's not quadrants 1 and 3.
Quadrants 1 and 3 is where tangent's positive. Good. What reference angle? What family? Pi over 4. So I have pi over 4 here, and in the third quadrant I have 5 pi over 4. In general, can we write it together as 1? Yeah. How? Pi over 4 plus pi. This time I'll use a k, where k is my integer. Sometimes you'll see k, sometimes you'll see n. Any questions there? Understand the difference between when you can divide and when you can't divide. Okay, let's look at those examples that you did that were in the book, just to see if there were any like parts in there. And then we'll come back, we'll do one graph. But example 4 was sine of theta is negative root 3 over 2. Did that one go okay? Figuring out the family, the quadrants, getting the answer. What did they do in example 5? What'd they do?
They gave a restriction.
Okay, well they gave a restriction so we know we want specific solutions, so we know what the directions are. But how did they go about changing this at the beginning so we could solve it? What'd they do?
They use an identity.
They used an identity, yep. Why didn't they use the one that had the cosine squared in it? Exactly. If there's already a sign in there, if you get a sign squared, then you can get one side equal to the most beautiful number, which is 0. And then you can factor, and then you can solve it and get your solutions. Okay? Any questions there? So if you wondered what they did in that step, they used an identity. And that identity is a good one, okay? What about the graph? We'll talk about the graph ones in a minute. They did a cosine, they did a sine, good. They stuck with, we don't see a whole lot of tangent and cotangent graphs, nor do we see a lot of the reciprocal graphs. It's normally sine and cosine. We may occasionally see a reciprocal one, but if you saw a cosecant graph, wouldn't you anyways have to do the sine first? Yeah, and if you saw a secant, you'd have to do the cosine first. So before we do a graph, let me just tell you about those identities. Because you're going to see the cheat sheet was on the homework for the past 2 nights. You want to make sure you have a really good cheat sheet this week, okay? So make sure you have that. These are things that I'd probably put on it. Reciprocal identities, quotient identities, Pythagorean, that shouldn't be an M, even, odd, and those double angles, we saw 3 of them today. 2 in the examples we did, 1 in the book. Okay, the other form is cosine squared minus sine squared, so they use those. Okay, so those are ones that you want to make sure you have on that cheat sheet. So homework's going to be make sure you have that. That's not on tonight's homework, but you should already have it done. But if not, make sure you complete it. You're finishing pages 15 and 16, right, in the packet. So that was on last night. It's also on tonight. Answers are in there. And then you're going to finish some of the problems that are on solving and graphing. So we're going to do one graphing. Do we have any volunteers to do a problem for us for tomorrow? Number 35, I see two, there we go. So 35 and 39, okay, perfect. And let's do a graph. Let's just do the first one. And like I said, you're not going to this year have to do these terrible graphs with them changing A and B and C and D and doing all this crazy stuff. Most of the problems that I've seen that are on the AP test that revolve around trig function graphs, they're normally calculator questions, and they often will give you the graph or allow you to use your calculator, okay? So let's make this one a little bit more interesting by putting a 2 in front of it. And we won't change the sinusoidal axis. If we added or subtracted, we'd slide our graph up and down. But we'll just do this with the x-axis. The 2 out in front, that's called the amplitude, which means how high and low your graph goes. Now your cosine curve, normally, you remember a cosine curve, because we want to remember a cosine and a sine. Cosine curve starts high, ends high, goes from 0 to 2 pi. If we're bumping it over, some people might look at this and go, okay, I just shifted pi over 4 to the right. Some people do well with that. Some people need a little bit more concrete. So a way to concretely figure out where you start and end, you always take what's in parentheses after the trig function and set it equal to where it normally starts and where it normally ends. What that will do is help you get a beginning and an end for just one period of the graph. So if you ever have something messy in parentheses, if you just set that equal to where the normal period starts, normal period ends, no matter which trig function you're dealing with, it works. And then it also helps you figure out a good scale. And I would count by pi over 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I could graph from pi over 4 to 9 pi over 4 and graph my equation for out of here. Yeah. Okay, so you have just a couple graphs because we're not going to spend a lot of time on it, but try those in the homework. If you have questions, I'm normally here after school, here during homeroom, so please make sure you come and see me. And have a great day. You guys are a little quieter than fourth period. Let's see.